Hello students, welcome back. We talked about the local equivalence, and here comes an example problem. Find a power function that shares the same local behavior. I should say a shifted power function that shares the same local behavior as the given polynomial function at each zero. How many zeros are there? There are 3. X equals to -1 here with multiplicity. What's the multiplicity? Multiplicity 1. And x equals to 3 with multiplicity 2. And x equals to -5/2 with multiplicity 3. So those 3. So we have to do this problem 3 different times. And here we go. At x equal to -1, we have this computation. Plug in x equal to -1 to all these. And then plug in x equal to 3 to this one and that one. And then plug in x equals to -5/2 to these and this. In the end, we get these expressions. Too tedious? Yes, I agree, they're tedious. Not difficult, but they're tedious. Here's a visualization here. The original function, and plug in x equal to -1 to all these, and then you get this linear function. Compare the linear function and the behavior of the graph. As you can see, they are locally equivalent, so that the graph of the original function, the blue function, behave the same. Cuts through the x-axis like a line. The numerical computation of q of c is not that important, to tell the truth. All I care about is negative times x plus 1, so cutting through x equal to -1, and it's negative times that, so going down. Around x equals to -3, this is the main part, and plug in the numbers, and we have something times x minus 3 squared. So this is gonna be upside down U-shaped. And here we go. Blue is the original, and red is this shifted power function. And then zoomed in a little bit, zoomed in even further. Again, this number is not that important. Negative times this power, which means upside down U shape. That's about it. How about the next one? X equal to -5/2, so that's the main part. And plug in the value here and there, and that's what we get. And then we end up with this. Of course, I used computer algebra system to calculate this. And then what do we have? Basically, positive times cubic. Therefore, we get this kind of graph. Curved, slow down, but increasing. So blue is the original, red is the shifted power function. Compare these two. They don't really resemble each other, but locally they behave kind of similarly. And as you can see here, if you zoom in further, they became kind of indistinguishable. That's the local equivalence in action. Okay, now that we went through the local equivalence concept and went through some example problems, let's go to the conclusion. So here's a summary version. If you have even multiplicity, then we have to have the same sign around x equal to c, the 0. So hit the x-axis and bounce back up or bounce back down, because we have to have U-shape, either upside down or plane. So you have to have something like this. Green is the polynomial function. Hitting the x-axis and bouncing back up. And locally, it's kind of behaving the same way as this shifted power function. And then that's the other way around. So even multiplicity, you can visualize kind of like this. You can even sketch it with paper and pencil. And actually sketching is very good because, your brain is connected to your hands. So if you do sketching and then writing, it really enhances your understanding. Now, what if the multiplicity is odd? In that case, we have to have a sign change. Cross the x-axis and increase, or cross the x-axis and decrease. So like this, from negative, cross the x-axis and increase to positive, or positive, cross the x-axis and decrease. Either way, we have to have a sign change around x equal to c. So that is the conclusion. Even multiplicity, no sign change. If one is plus, the other is plus. One is negative, the other is negative. And the graphical justification, here they are. Alright, we have some constant q of c times x minus 2 to the even power. So we have the same sign, U-shaped, hitting and bouncing back, U-shaped, hitting and bouncing back, whether it's forward U-shaped or upside down U-shaped, either way, it's bouncing. When m is odd, it's crossing. Negative, cross the x-axis and becoming positive, or vice versa. Positive, cross the x-axis and becoming negative, either one way or the other. Now let's use these ideas to some polynomial inequalities. Okay, here we go. Solve the given inequality. Now let's do it in an easier way using graphs. And then we're going to do this to local behavior on zeros using diagrams. Which method is more important? The diagram method is going to be more important, even though it's a little harder. Why? Next week, we're going to go to rational functions. Then the graph method will become highly inefficient. Plot a graph and then you can't see what the heck is going on. Then what's the point? Here in polynomials, graphs actually make sense in many cases. And even if it doesn't, it is possible to zoom in appropriately and then see the behavior. So it is a little bit of a less motivation. But nonetheless, we're going to focus upon the diagram method anyway. Okay, here we go. So we have x equals to negative 1/2. There goes 1, 0. And then x equals to 1. And then x equals to 2. We have 3 zeros. And these 3 zeros divide the number line into 3 pieces. 4 pieces, excuse me. These 3 dots divide the number line into 4 pieces. And we have to check each interval. Now, plug in some humongous x value here, like 100 or something. Then everything is well positive. Do you see that? Unless you have negative sign up here, you're going to get positive here in this region, in the right-hand side interval. And then cross this, and we have to have sign change because this is odd multiplicity. Cross this, we have sign change because again we have odd multiplicity. And then we have another sign change because we have odd multiplicities all the way. And then we are looking for this thing to be greater than 0. So let's find out positive intervals. Where are they? Here and then there. So put them together. Here we go. Between negative 1 and positive, between negative 1/2 and positive 1, or strictly greater than 2. In the interval notation, you can write like this. By the way, here's a graph. And then graph actually gives you a pretty good idea. From negative 1/2 to positive 1, above the x-axis, so positive. From 2 to infinity above the x-axis, so positive, greater than 0. So graph method is not bad at all in this case. But if you go to next week, the graph method will not work very well. Yet the diagram method, it will continue to work. That's why I'm emphasizing the diagram method. I'll be more time? Okay. I'll be more time. One more here. Okay, how do we handle this? How many zeros are there? I see 4. X equals to -1. X equals to 0. X equals to 3/2. And x equals to 3. And then they have appropriate multiplicities. So how do we work out? Stop the playback and try to graph this diagram. Get the number line and plot those zeros and mark the multiplicities. Okay, here we go. These are the zeros. Okay, draw the diagram and mark the multiplicities. So 3 here, that's odd multiplicity. So we have to have a sign change. 3/2 here. Third power, so that 2 is odd multiplicity, so we have to have sign change. At x equal to 0 here, we have nothing here, so first power, so odd multiplicity, so we have sign change. And finally, x equal to -1 here, second power, that's even multiplicity, so no sign change. Keep the same sign. Start from positive, because if you plug in some humongous number like 1,000, then everything is well positives. So to the right hand side, 99% of the time you're going to get positive sign. Of course, unless you have some negative signs sticking around. So plus, and then cross odd, cross odd, cross odd, and cross even. That's how we get all these signs. And then in the end, what do I want? Less than 0? Okay, so I want negative intervals. 1, 2, 3 intervals. So x is less than -1, or between -1 and 0, or between 3/2 and 3. Here's the interval notation. And by the way, here's a graph, and in this case, graph makes a lot of sense. Less than -1 here, between -1 and 0 here, and then between 3/2 and 3 here. The graph actually makes a lot of sense here in this case. If I remember correctly, graphs are all okay for this set. Next week, no longer the case, so you really have to use the diagram method. Let's see, one more time. Okay, alright, just one more, let's do E. Okay, this time this is not given in the factored form, so you have to work out and factor it first. So go ahead and factor it. It'll turn out we have this complete square, and then simplify, alright, x plus 2 squared, x minus 2 squared. And that thing is less than or equal to 0. Okay, alright. We have two zeros, x equal to -2 and x equal to +2. And then they both have even multiplicities, so no sign change. So starting from right hand side, plus, same sign, there you go. And this is less than or equal to 0. No negative intervals, so it looks like no solution. But be careful. This is semi-inequality, so equalities is allowed. So x equal to -2 or x equal to 2. Alright? If this had been strict inequality, then no solution is correct. But semi-inequality, that's a little bit tougher. Here's a graph. Doesn't go down at all, so strict negative doesn't happen. But x equals to -2, that's when y coordinate is 0. X equals to +2, again, that's when the y coordinate is equal to 0.